You're on day 3, solid. So there's a couple different types of solids. You're going to deal pretty much with crystalline solids. Right? And these are composed of atoms. Or molecules. Arranged in structures with long range order. So we have long range order. So there's, you guys probably know glass. Glass is another solid, right? But it doesn't have long range order. We're going to only talk about the ones that have long range order, and we're going to talk about 3 of the ones that have long range order. So the easiest one. We can use X-ray crystallography which uses diffraction to determine the arrangement of atoms, which of course we call it the crystalline lattice. Because it's a repeating pattern. All right, so X-ray crystal is a very, very solid technique to determine what you made, right? Because when you make a lot of things, you can't tell them apart. If it's supposed to be green, like a green crystal, you have a green crystal, or an orange crystal, or a red crystal, or a white powder, like whatever it is. Like I got this crystal, like what is it? And it's hard to tell sometimes because you might want to change a couple elements or a part, change part of the compound, and you don't know if you made it or not. The structure helps determine if you made it or not. All right. So now there's something with this called the unit cell. And the unit cell is the smallest unit in the crystal. Right? And from the unit cell, you can generate the entire lattice. All right. All right. So with this unit cell, like the unit cell is, think of it as a cube, because we're only dealing with cubes. It's true, it's not cubes, but we're just dealing with the cubes. A cube is a 3-dimensional shape, or all, all 6 sides are the same, all 90-degree angles, right? And so you guys know what a cube is. And each of those corners of the cube, of the 8 corners, are, they can, it's almost like they can connect to another cube. You can build the whole lattice with these cubes, these unit cells, right? And so this is a 3-dimensional array of atoms, ions, and molecules. And so atoms, when they're in a unit cell, they're held together by intermolecular forces. Molecules are also held together by intermolecular forces. The ions, you can think of lattice energy. All right, why they're staying together. All right, and so we're going to deal with cubic unit cells. Right, and so these are all going to be cubes with 90-degree angles. All right, slash corners. So all cubes. And there's 3 of them. There's going to be 3 that we're going to deal with. Simple cubic, body-centered cubic, and face-centered cubic. Those 3. So if we look, simple cubic would have we did the lattice. Looks something like this. So you have atoms in each of the corners of the cube. All right, and that's it. Now, really what would happen, these are more nuclei. So think of these blue circles as a nucleus. And the atoms would actually touch. So if I could draw, like, for this guy, make it like there's one atom that's halfway there. And then there's the other atom. Oh, I do. Right, so the atoms actually touch on each, face side, right? Just like this one would touch there too. Right, so my drawing is not to scale, I apologize. But that's what we're talking about. So the atoms would actually touch, obviously the nuclei wouldn't. And your book actually has some pretty good pictures of these, believe it or not. So, erase my highlight there. Oh, actually, we'll keep those 2. All right. So there's simple cubic. Now, we'll learn that there is only 1 atom per cell here. Even though you've drawn 8 nuclei, right, we learned that overall there's only 1 full atom in the cell. It's 6 coordinate, which means there's 6 neighbors around it. So there's 1 above, 1 below, 1 in front, 1 behind, and 1 to the left, 1 to the right. So it's actually 6 coordinate. The edge, so this would be the edge of the cell, right? And all the edges are the same, right? It's a cube. So the edge length right, in terms of R. R is the radius of the atom. The edge length would be E equals 2R. Whether it's a lowercase or uppercase doesn't really matter. And for the simple cubic, it is about 52% efficient. That means just over half of the cell is full of atom. Most of it is, or almost half of it's empty space. And you've probably seen this before, especially if you played any type of sports with any type of round ball that you would be able to play. It's like whether it's baseball, softball, basketballs, volleyballs, tennis balls, etc. You know, when you put them into a container, there's always space between, right, the balls. Just the way it works. So whether it's ping pong balls, right? Now the smaller the ball, the less space, but it's still, right? Basketballs are hard, like you get, or soccer balls, right? They don't always go into the bag. They don't take up all the space. There's always room between the balls because they're round. All right. Now, body centered is going to look very similar with one little exception. We got atom, 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 atom. All right. So I'm going to draw the same basic cube by nuclei here. Now I'm drawing it as a different color just to show. Then we have one nuclei right in the middle. So in the center of the body. All right. So now, again, these are nuclei, so the atoms are still touching on the sides, on the edges. Actually, they're not touching on the edges anymore, though. They're close. So if we look, we had this one. And I did a green here. There is actually a gap here. They do not touch anymore. They actually touch this one in the middle. Both of them do. All right, so yeah, my drawing's horrible, I understand. But they actually touch there. They touch in the middle. So they do not touch on the edge anymore. Okay. We'll learn that there are 2 atoms per cell. It's 8 coordinate. So you have now 8 neighbors. And the edge length is E equals 4 times the radius over the square root of 3. And if you're really good in geometry, you might recognize some of these, edge lengths with the cube and whatnot. It's approximately 68% efficient. So more space is filled up. All right. The last one is face-centered. So same basic cube setup. All right, so we got the cube. All right, in the face now, here, there's one on each face. That should be, yeah, I'll make it just a little bit. All right, on the face, in the middle. So now, instead of, there's still going to be a gap there. Right, so there's going to be a gap again, but they're going to go from, if I have the blue one here, again, the one in the center of the face, I draw it, and it's not really in the center, is it? Again, try that one more time, try to get it in the center. There we go. So you gotta goes across the diagonal face to get the radius. So let's look at some lines here. That's 2R right there. 2R. Oh, twice the radius. Right, our radius goes from one corner through the middle to the other corner, and it's 4R. And this would be also 4R, because there's 4 radius you get there. You get a radius, diameter, radius, radius, diameter, radius. All right, so for face center, there's 4. Das, what's the question?
So I've noticed that these are like building upon the previous one. So on that face-centered cubic, does it have an atom in the middle like the
No,
body-centered cubic does?
does not.
Okay, so it doesn't. Okay, thank you.
Nope, you're just on the face.
Okay.
So there's 4 atoms in the cell. All right, now we're going to show you that how to determine that in 2 minutes. All right, you actually 12 coordinate. All right, the edge is equal to 2 times the square root of 2 multiplied by the radius. All right, so sometimes I get as your book has the R right there. I don't like it because it's hard to tell. Right, you can see it as 2R square root of 2 R as well. See that way too, and it's 74% efficient. Oh, again, your book has a little better drawing of pictures than I can draw. Better picture I can draw. So you'll see where the atoms touch and where they don't touch. All right. How am I determining how many atoms? Let's do that. So how to determine the number of atoms in a unit cell. All right. So let's look at this unit cell right here. And then we're going to have another cell there around it, another cell there, another one here, there, there. All right, so there's 9 unit cells right there. All right, so obviously if I'm totally inside the cell, right, so we're in the center, right, the whole thing is in 100%. All right, so there's something, so say this is the top view, it's called the top. All right, there's something called a lattice point. The last point is a point in space, right, occupied by an atom, ion, or molecule, whatever we're talking about. So if that last point is inside the unit cell, whether it's an atom, whether it's an ion, molecule, if it's totally inside, the whole thing counts for in the cell. All right. If we're on a face, so if I'm on the face, well, it looks like half of this purple cell, the atom, is in the cell, and the other half is in the orange. So 1/2. Half of it's in the cell. It's kind of like if you're in a doorway, 1 foot in, 1 foot out. Half you is in the room, half you is out of the room. All right. Then there's the edge. On the edge, we use blue for the edge. Well, it looks like I'm in 1, 2, 3, 4 unit cells. Right? So each edge is a fourth. And there's one more spot that we'll talk about. And that would be there on the corner. So on the corner, whether it's the top corner or the bottom corner, you're in the 4 unit cells. Right? So let's say we're on the top corner here, the top corner on the right-hand side. We're in these 4 cells, but there's also 4 more cells on above. So it's 1/8. It's in actually 8 different cells. That atom split into 8s. Which, like, wow. But if you think about it, right? I have on the plane I'm in, I have 4 other cells, and then above me there's a cell, another unit cell above me, and then the other 3. So there's actually 8 cells this is in. So it counts as 1/8. So that's why each corner, we go back up here, each corner counts as 1/8. These are all 1/8, right? Because they're on a corner. So that's 1, 2, 3, 4, 5, 6, 7, 8. 8 times 1/8 is 1. Josh, you have another question? No? Okay.
No, I forgot to turn or put my hand back down.
Yeah, all right. No problem. It just buzzed me.
Well, Bree had a question.
Bree, you have a question?
Yeah, I'm just confused on how you got 1/8. Like, so I just would like if you could further elaborate on that. Just considering like the way that you put it is kind of like confusing me on how you got 1/8 for the corner edge.
Right. So let's look at this right here. Okay, so it's obviously in the one shown, right? That atom, how it goes in this atom, this unit cell shown. There's also a unit cell right next to this unit cell, and there's 2 behind it. And so I could, like, so there's another one that kind of comes this way, right? There'd be another one here, and there's 2 behind them, right? If that makes sense. So there's 4 right there. And then on top of these, there's another one here, another one here, another one here, and another one on top. So there's 2 layers it's in between. All right? Because if you have 8 cubes coming together at that point. I don't know if I have a better, let's see, do I have a better picture of this? I don't think so.
I get it now. It was just the 2D from the 3D was just a little bit confusing.
Yeah, I get that.
So that
Let me see something though. Where is yes. All right. So where is okay. All right. Okay. Let's see here. Where is all right. All right. So let's share. This one. All right. So hopefully we can see this now. This is the simple cubic. Nope, you can't see. There it is. All right. So here's your book's picture of the simple cubic. Right here, in where the mouse is going, that pointer, if you can look, you can kind of see the cell we're talking about. And each of these corners is where the nucleus is. The cutaway is over here. So we just made the cell. So I have all 8 atoms, and there's my actual cell if I cut all the excess away. So it's 1/8, 1/8, 1/8, 1/8, 1/8, 1/8, 1/8. All right, because they're at the corners. Because right here, if you look at this one in the mirror of the 8 cells, it actually has 4 cells on the bottom and 4 cells on top. So that's how that one works. I don't know. Change photos. You'll see it. Can you see it? No. Change photos. But here's body centered. Here's body centered, and you can see the gap I'm talking about between the atoms because there's one in the body. Now, the gold one, assume it's the same atom as the purple ones. That's not always clear. It doesn't have to be, but just right now, assume it is. They're all the same size. It's just how they're arranged. So this is where we go from one corner to diagonal across. Doesn't matter what corner. So if I'm in this front lower right corner, I have to go to the upper back corner to actually have something touch. A radius, a diameter, and a radius. All right, so these books actually show you, or the pictures in your book do a pretty good job of trying to show you this. A little bit better than I drew. Just a little. All right. So back to OneNote. So that's how we tell how many. So if I have 8 corners times an 8, if I have 2 faces times a half, if I have 4 on the edge times 4, whatever we have, we add them up pretty easy. Like, again, that's not going to be. The goal is not to confuse you. All right. So when we talk about packing, your book goes into closest packed. Right? And this happens when bonding can be non-directional. Think oranges in the grocery store. Right? You have oranges, no matter where, they're going to fill in and just going to be arranged accordingly. The oranges are not going to be directly on top of one another. Right? So there's 2 options that your book goes on. It goes through hexagonal. I'm not spelling very well right now. Closest packed. And cubic. Closest packed. We're not going to do with hexagonal because that's a hexagon. The cylinder with a hexagon. We're not going to do it. But the A, B, A. Layers A, layer B, layer A. Where the third layer, so the third A, is directly below the first A. All right, so if you have oranges, and you have oranges in the, I'm going to call it the holes, right? So the oranges being right on top of each other, they go in the holes. So oranges are offset. And then the next layer is right back to where the top layer was. All right, kind of how that works. Cubic is A, B, C. This is where the third layer is offset. from first. Now, that might sound bad, but it's very similar to face centered. So we'll use face centered cubic to use that. All right. So all we're going to do is simple cubic, bicentered cubic, and face centered cubic. All right. So now let's talk about these. Well, what am I going to do with these before I get into the actual solids? We're going to have to know how many, we can use the density to figure out the size of the atom. It will do some problems. It's actually simple conversion, and we're good to go. All right. So if you don't know, we haven't done it. Once we do the examples, they'll be a lot easier, a lot better to explain. All right. So let's talk now. Again, I'm not going to do anything with the hexagonal closest pact. And the cubic closest pact is the same as face centered, so we're just going to roll with face centered. All right. So crystalline solids. Three types: molecular, ionic, and atomic. All right. Obviously, molecular solids would be composed of molecules. All right. Ionic solids would be composed of ions. Atomic solids, there's three types of atomic solids. There would be metallic, there would be non-bonding, and there'd be covalent. Which is a covalent network. All right. So molecules, they're held together by intermolecular forces, right? So ionic compounds are held together by Coulombic forces, charges. Metallic solids are held together by metallic bonds. Which is a delocalization of electrons. All right. We don't really go into much of that. The non-bonding atomic solids are held together by intermolecular forces. And the covalent networks are actually held by covalent bonds. All right. So molecular solids typically have low melting points. Low melting points. Let's write that out. All right, think ice. Think carbon dioxide, right? Cold. They're usually, most molecular solids are brittle, and they're non-conductors of heat and electricity. And ice is actually a pretty good insulator. Some of you guys know that. All right. So ionic compounds, they typically have higher melting points. Think for NaCl, it's 801 degrees Celsius. That's pretty warm. Now, ionic compounds are typically brittle or hard, but a lot of times they conduct. All right, so that's molecular, that's ionic. Now, atomic. We talk about atomic, we got metallic, right? They have variable melting points. It depends. Like liquid, mercury's all liquid at room temperature. Gallium melts in your hand, and some things melt pretty hard, pretty high. Now, metallic solids are, as you guys know this, malleable, which means you can hammer it into sheets. They're ductile, draw it into wires, and they conduct heat and electricity well. Non-bonding atomic solids, intermolecular forces, are held together, right? They're held by intermolecular forces. They usually have low melting points, like xenon, right? Very low melting point. They're brittle and non-conductors. All right. Covalent bonds, these covalent networks, they usually have very high melting points. All right. Think about diamond, quartz. All right. And they're hard. They're very hard, and they're semiconductors. And so these covalent networks are one of the strongest solids we can get. If you think about diamond and whatnot, there's also silicon carbide. There's some boride compounds that are pretty hard. They make covalent bonds, and they're very hard. All right. So, whereas ice is held together by hydrogen bonds, which are much weaker than regular bonds. Diamonds held together by a covalent bond between carbon and carbon, much stronger. All right. So let's look at ionic compounds first. All right. These are typically are similar to simple cubic SC, bodied centered cubic BCC, or face centered cubic FCC. All right. That's usually how we can, get them. So they have cations and anions. Right. So we got positive and negative. The cations are smaller, right? Because we lost volume, because the volume is due to the electron, and anions are larger. So that means The cations are usually in holes, and the anions are in the lattice points. So, for example, zinc sulfide. Sulfur is face-centered cubic. Zinc is in, we're going to call it tetrahedral holes. And there's a picture for that in your book. And so zinc looks like it's tetrahedral, right? There's got 4 sulfurs around it in the tetrahedral, and it's in the so we're going to call it in a tetrahedral hole versus the sulfur. It's still 1-to-1 ratio, zinc to sulfur, but it's the the cation is usually in between the anions. It fits in that space, in that empty space between. And just how it happens to work out on, we're not going to get into that, but that's what's kind of going on there. All right. And so a lot of times the anions are going to be one of our, body-centered, face-centered, or simple cubic, and the cations will just be in between somehow, whether it's octahedrally, tetrahedrally, or something else that we haven't really discussed yet. All right. But again, I'm not going to make it, you don't need to memorize what compounds are which or anything like that. That's not important. Then there are the network solids that we talked about. Highlighter. All right, then cover out networks. We got carbon and graphite. We got diamond and graphite. All right, they're allotropes. All right, which is one or more forms of the same element, like O2 and O3, oxygen gas and ozone. All right, so diamond, as you guys are probably aware, right, it's tetrahedral, sp3 carbon. It's hard. It's got a high melting point, and we use it to cut all sorts of things. Graphite is trigonal sp2, right? And it's more used, I can spell today, right? To write, for pencil lead, lube, right? Sometimes there's some graphite lubrication that's not oily. And how does this work? You have these hexagonal trigonal sheets of graphite. Right? And then below that one, let's draw this good. I'll draw it here, 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 and here, 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 here. All right. So what happens is you have the unhybridized p orbitals on these carbon atoms, right? They're sp2. There's an unhybridized one. Well, what happens is that the blue ones meet up with the green ones, and there's interaction between them. All right. So graphite is actually soft with a low melting point, and the p orbitals, the pi system, the pi bonds actually can interact from layer to layer, and so you can just take layers off. That's why writing works with the pencil, because you're taking the layers off. You're just taking layers and upon layers of carbon off, and you stain graphite. Kind of neat. All right. Okay. There's also for carbon. There's also fullerenes. So that's carbon 60, and that's where carbon is in each vertice of a soccer ball. So you got the soccer ball with pentagons and hexagons. Each vertice would be a carbon, and that would be your carbon 60. And we also have nanotubes. And those are carbon 6 C6 rings with closed ends. Kind of neat. All right. Next, silicates. What goes into silicates? So that's SiO2. So in quartz, silicon is tetrahedral, which gives us long range order, which is great. Glass, all right, is also SiO2, but there's no long range order, right? We call it amorphous. All right. Sand is also another type of SiO2. All right, but that's just more of a just smaller. Glass and sand are very common, very similar, but I don't think your book goes into sand for whatever reason. If I want to make glass stronger, you add B2O3 to make borosilicate glass under the patent name of Pyrex, because Pyrex came up with that. All right, and so just pure glass shatters really easily. You use Pyrex, and it makes the glass more durable, better to heat, or thermal expansion, where they get hot and they heat up, cool down, right? And then they shrink, and it doesn't shatter as easily. So silicates are another example. And the book has some nice pictures of them. We're not, but again, you're not going to have to determine the difference between them and all that stuff. A couple more classes of solids here. So some of you guys might like this, ceramics. Hey, you guys get to do ceramics. We all got to do, at least I did. My kids are doing ceramics and art and elementary school. I get to make something and put in the oven. The ceramics are inorganic, non-metallic solids. Prepared from powders mixed with water, shaped, and then heated. And when they're heated, there's chemical and structural changes, right? It's not necessarily as much of a, I guess, I mean, you can almost call it a chemical reaction because you're changing the bonds. You're changing how it is bonded, the direction of bonds, where bonds are occurring and whatnot, right? And so it's a process. Now, what are ceramics? Things from bricks, there we go, bricks, tiles, a lot of pottery, a lot of dishware, a lot of insulating elements, and electronics. All right, so that's a lot of ceramics, and some people really like ceramics. I know art at Coastal here, you get to make ceramics. It's kind of fun, and some people really like that. Another thing that your book goes into is cement, which is a mixture of CaCO3, limestone, SiO2, silica, Al2O3, alumina, iron 3 oxide, and calcium sulfate dihydrate, which is gypsum. You might have heard some of these before. Then you add, a lot of times you have to add sand, water, and sometimes pebbles. Right? It's a reaction with water. And you get SiO, Si bonds forming. And it actually cures, and you want to slowly let it dry. And there's different types of cement. And if you go to the hardware store, you'll see there's a bunch of different types of cement. And you can have different, you can have kind of a weak cement if you wanted to. You can have a very strong, thick cement. It depends on what you want to do. But we're just telling you the basics behind it. This is just the I guess the big picture view, what it kind of is. All right. We're not going to go into much more. I'm not going to test you on different types of cement. Right now, if you're in a masonry class, it's a different story, but we're not. All right. 4 topics, and then we'll do some problems. The first one is semiconductors and band theory. All right. So, a lot of times in Chem 1, especially, like I already covered this, molecular orbitals. MOs. Right? What happens is when you have atomic orbitals combined, they come into a molecular orbital, according to this theory, and you get one that's lower in energy, that's bonding molecular orbital, and one higher in energy, that's an anti-bonding MO. right? The bonding MOs we call the valence band. And the anti-bonding MO we call the conduction band. And the difference in energy between them we call the band gap. All right, so let's look at how this works. If I had relative energy, lithium, I have lithium, lithium. I have lithium down. Why do I have lithium down like that? Where is okay, there we go. Yeah, it's 2S. Okay, there we go. That's actually a pretty good picture. That will just show that. Oh, no, I don't do that. Okay. All right. Oh, where'd it go? I'm sorry, guys. My pictures are the full size of the screen, and I can't do anything on the screen. So let's do that. Okay. Do that. 2, and here we go. Right there, and share. Sure. And there it is. Let's see. You see it yet? There it is. All right. So you got Li. It's got its valence band, right, as 2s1. And then if you have 2 lithiums, 3 lithiums, 4 lithiums, N lithiums. So you think what a mole is, right? So if you have 7 grams of lithium, you have a mole of lithium. That's 6 times 10 to the 23rd atoms. So there's a huge amount of atoms, a huge amount of valence electrons that we get into this this valence band. All right. And so that we talk about the bands. There's the valence band and the conduction band. So let's go back to our OneNote. All right, let's try to draw it. If I have lithium here, Li, I get 2s. There's a 2s orbital with 1 electron. Li2, I got 2s with up, down. All right. And what happens is, as I get Li4 in there, I get 2s, 2s. There's also now a up, down, up, down. There's also the 2s star, which is the anti-bonding. A lot of times we do a star is there. 2s star, 2s star. All right. And what happens is you get this conduction band, or valence band, excuse me. You get the valence band, and then you get a conduction band. And we call this right here, that distance is the band gap. Some elements or compounds don't even have a band gap. So let's look at the three options. There's conductors, semiconductors, and non-conductors. So if we have a conductor, I use blue, my valence band and my conduction band a lot of times look like this. A lot of metals are this way. All right, I'm thinking copper, silver, and gold. Great electronic conductors. They don't have a band gap. Semiconductors, right? Semiconductors have a valence band. And they have a conduction band. All right, and there is a small gap. So, for example, your first calculator probably was a solar calculator, if you have any solar things, right? And what happens is that band gap can be surpassed with sunlight. Sunlight has enough energy to move electrons from the valence band to the conduction band. Now, it gets a lot more complicated, right? Because this valence band is doped with either P-type or N-type. Right, so P-type would be positive, N-type would be negative. So P-type has less valence electrons, so N-type would have more valence electrons. So silicon's like the prime example. So silicon has 4 valence electrons, right? So an N-type would have more valence electrons. So a lot of times arsenic or phosphorus could be thrown in, even nitrogen, right? Something, one of those three, depends on, you know, stability and stuff. I don't do much with this, so I don't know which ones they use, but that would be the column. A group 15 would be one they would throw in. For a P-type, you'd have less valence electrons. Boron would be a great one to throw in, all right, to have what we call holes. So we have less electrons, and this builds up p-n junction. And your book kind of goes into it and really helps with the semiconducting. You get that sunlight and pushes the electrons, you know, and make them happen, make the circuit happen. All right, so semiconductors have a small electron gap or small band gap. Non-conductors, valence, and then they have the conduction band. And this is quite large. All right, they don't conduct at all. All right, and so semiconductors are kind of neat because they can conduct with the right input. Conductors will always conduct, and non-conductors do not conduct. And semiconductors, we can control whether it conducts or not. That's why they're used so much in electronics, which is fun. All right, but we're not going to go dive into it. I mean, you can go way down that rabbit hole. We're not going to go down it. Most of this stuff you can go down. You can get PhDs in solid state chemistry and not even do, like, you can just do semiconductors and that's it. So that's what they are. The last one are polymers and plastics. Polymers and plastics. So a polymer, think of poly, many, are long, chain-like molecules composed of repeating units called monomers. All right. They're generally amorphous, but can be crystalline. All right. So one that you're familiar with is polyethylene. And that is an addition polymer. And what does that mean? That means it links together without loss of atoms. So we don't have to take any atoms out. So for example, one polymer that we're all very familiar with, not necessarily that it's necessarily a polymer, but we're very familiar with, would be like carbohydrates. A lot of us like carbohydrates, right? Pizza, spaghetti, noodles, mac and cheese, right? Well, you take a simple sugar like glucose or fructose, any of these simple monosaccharides, and you add the sugar up, like sucrose is a combination of glucose and fructose, right? But there's a water that links them, right? And so when we add those two, we lose the water. When we separate those two, water is needed to separate those two. And as we link up sugars longer and longer and longer, they become carbohydrates, right? That's why we like them so much. So, all right, and so that's another, that's a polymer. Polyethylene is an addition polymer. We don't lose any atoms. Right? There's two that are there we know about. There's HDPE. All right. This is high density polyethylene. And this has what we call little branching. That means the chains of this polymer these chains of this polymer are close together. All right. All right. So that means there's high crystallinity, high density, good strength, and resistance. Then there's low density polyurethane. Not polyethylene, excuse me. All right, and these have more highly branched chains. Right, so you know most plastic bags are LDPE. I can't spell. Right, so low. Most you go to the grocery store, you go to the hardware store, you go to any store, and they give you that plastic bag or the one with that white one which says "thank you" on it or whatever it is, store logo. That's a low density polyethylene. All right. So the monomer would be C. Let's go with H2C, CH2. All right. And then when we put them together, all right, it becomes CH2, 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 etc. And so really it becomes tetrahedral almost. Almost, but it's not. It's not. All right, so that's the polymer. Another one that we like to see is PVC, Polyvinyl Chloride. That's HC, CH2, Cl. All right, and that, when it links up, I have H, yeah, that's right. Sorry, it's H. All right, so that's the monomer. That's how they link up. All right, and PVC pipe is pretty good, pretty common. And that's all the solids we're going to do. No twice. So now all we got to do is a couple problems. Don't get me wrong, there's a lot more that goes into plastics than this. Just that's the basics. That's the tip of the iceberg. All right, so now I want to work on the examples. It should say day 3 on them, and it has examples, because these are more of the questions you'll be asked. It says lead adopts the face-centered cubic unit cell in its crystal structure. It gives you the density of lead is 11.34 grams per centimeter. It asks what is the radius of the lead atom. All right, so face-centered lead. We first off know lead is Pb. Face-centered, all right, I have 4 atoms per cube or per cell. All right, the density would be 11.34 grams of lead per 1 centimeter cubed. Radius, so edge equals 2 square root of 2 times the radius. All right, that you can look that up, right? That's just from the notes here. Whoa. All right, 2r square root of 2. 2 times square root of 2 times r. All right, so I know I have lead. I know I have 4 atoms per unit cell. All right. So if I have 4 atoms of lead, what do I have 4 atoms. So that's what I'm really starting with right here, is just the 4 atoms. We know atoms of lead go on the bottom. Has to. What should we go to on top? Well, I kind of want to know a volume of my cell. So if I get my unit cell here, right? If I get the unit cell, if I get this edge length here, doesn't matter if I get that edge length, doesn't matter, all the edges are the same, right? They're congruent. That I can figure out the radius, because I know the edge length, I can get the radius, because 2 times square root of 2 is a number. So I have a volume here, right? I have a volume, so, and I have mass lead. Can I get the weight of the 4 atoms of lead? Is there a way to do that? Well, probably, right? So many atoms of lead would be 1 mole. That's, of course, 6.022 times 10 to the 23rd atoms of lead is a mole. Then we know 1 mole of lead is 207.2 grams of lead. Then we know that there's 11.34 grams of lead in 1 centimeter cubed. So there we go. 4 atoms of lead, so 4 times 207.2 divided by 6.022 times 10 to the 23rd divided 11.34. I should get 1.21 times 10 to the negative 22nd centimeters cubed, and that's my volume. So the volume of my cube. And that kind of makes sense, right? You would think that 4 atoms of lead would be very, very small. Right? I mean, kind of makes sense. So then, I know that the volume is length times width times height. And we know that the length equals the width equals the height, because it's a cube. All right, so I have to take the cube root of the volume. Gives me the length or the width or the height, which we call the edge. So I take the cube root of 1.21 times 10 to the negative 22 centimeters cubed. If I do that, so my TI-83 that I have, that's as old as some of my students, I just hit math 4. That gives me, or I can go to the 1/3 power. I hit second answer, and I get 4.95 times 10 to the negative 8 centimeters. Well, that's the same thing as 4.95 times 10 to the minus 8 times 10 to the minus 2 meters, right? Because sign is negative 2, which is 4.95 times 10 to the negative 10 meters, or 495, 495 times 10 to the negative 12 meters. Well, that's where we like to go, because it's 495 picometers. And a lot of these are in picometers. So That's an easy way to convert from picometers. You can go centimeters to meters, meters to picometers. I don't care how you do it. But the answer is probably going to be in picometers. It doesn't say that, but that's what it's probably going to be in. All right. So I got the edge length. So now the edge, E equals 2 square root of 2 times R. So 495 picometers equals 2 square root of 2 times R. So R would be 175. Does that work? All right, so what did we do? We found out how many atoms were in the cell, right? And that was from it being face centered. Then we found the volume of those 4 atoms using the density. I found the atoms, I found the mass, then I found the volume using the density. Then I found the edge, because it's a cube. And then we used the formula from the book to figure out the edge length in terms of R. That's it. The next one, very similar. A and B, right? There's just 2 different points. We did it not much different. So crystalline molybdenum. Molybdenum is MO. So MO, and molybdenum weighs 95.94 grams per mole. Body-centered cubic unit cell. That's 2 atoms, right? And the edge length in terms of R would be edge equals 4R over the square root of 3. Again, you do not have to memorize that. It's just one of the formulas. It gives you a density. And that density is 11.28 grams of molybdenum per 1 centimeter cubed of molybdenum. So it's going to be almost the exact same thing, except I'm not starting with 4 atoms. I'm starting with 2 atoms because I'm body-centered. So 2 atoms of molybdenum multiplied by, well, we know there is 6.022 times 10 to the 23rd atoms of molybdenum in 1 mole. And we know 1 mole of molybdenum is 95.94 grams of molybdenum. And we know that there's 11.28 grams of molybdenum in 1 centimeter cubed. So that's going to give us our value. So 2 times 95.94 divide 6.022 times 10 to the 23rd divide 11.28. I get, hopefully you do 2.82 times 10 to the negative 23rd centimeters cubed. So there's my volume. Of course, the edge, well, no, not yet. Yeah, the edge of the cell is equal to the cubed root of the volume. So just go to math on my calculator for second answer, and we get 3.05 times 10 to the negative 8 centimeters, or 305 picometers. So all now I do is so that's A. For B, right, we got the edge is 4r square root of 3, or the edge times the square root of 3 over 4 is the radius. So that's 305 picometers times the square root of 3 divided by 4. I get 132. Is everything good? You guys all right? Good to go. Got a couple more and then we're done. All right, so the next one. Barium. Try it. Give you a couple minutes to try it. Try it. See if you guys can get it. See if you can get it. Right. So how do we do? Let's see. 2 atoms, right? So we get 2 atoms of barium. 6.022 times 10 to the 23rd atoms. It's 1 mole. And is 1 mole of barium is 137.33 grams of barium. And 3.59 grams of barium is 1 mole of barium. So I'm getting 2 times 137.33 times 10 23rd. I get 1.27. Oh yes, thank you. Dust, thank you. 1.27 times 10 to the negative 22 centimeters cubed. The edge is the cube root of the volume. 1.27 times 10 to the negative 22. So I get 5.03. 10 negative 8 centimeters, or 503 picometers. And so the edge is 4r cube root 3, or edge times cube root 3 divided by 4 is r. So r would be 503 times square root 3, 4. I got 218. Hopefully that's what you guys are getting. Hopefully. Hopefully. One more. Okay, that's it. One more. So this last one is the other type of problem that you guys would have to do. 112 here is an oxide of rhenium, because rhenium can have more than one charge. That's this unit. So rhenium is here. And oxygen are here. All right, so where are they at? So rhenium is on the corners. All right, on the corner. So each of these corners is an 8. And there's 8 rheniums. 1, 2, 3, 4, 5, 6, 8 rheniums. 8 times 1, 8 is 1. So there's 1 rhenium. Oxygen is on the edge. Right? It's on the edge. And so the edge, O, that's edge. And that would be what? 1/4. And how many do we have? I have, and just 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 12 times 1/4 will be 3, right? 12 divided by 4 is 3. So my formula will be RHO3. And that's it. That's all we want with that. So that's solids. That's chapter 12. That's all we have.